stability. The root, this one is saying that, so say right now, in the Routh Hurwitz criteria, and that can help us to determine whether the system is stable or not by telling the sign in the first column, the sign change in the first column, and then we combine it with our special case, and we know that basically this is the imaginary axis, and basically we're saying that as long as for the situation, for the common situations, if there's no repeated roots situations, then under that situation, if all the poles are located to the left of this imaginary axis is described by s equal to 0. Okay, so that is a vertical line described by this equation. So for the system without repeated roots, as long as all the poles are to the left of this, then we say the system is stable. Okay, and relative stability is this. Are we able to tell whether a system had all the poles to the left of this line? And this line is described by, say, s equal to minus alpha. Say this number here is minus, say, let me cope with my notes here. Okay, so let me make one number here. So for example, if this one is, this location is minus 1, so we want to know whether a system has all the poles located to the left of this line, and this one basically is as equal to described by as minus 1. So here we want to know is for relative stability, it means we want to know whether all the poles of the system locate to the left of, say, example s equal to minus 1. Okay? Because if, say, all the poles are located to the left of minus 1, we can say the system is more stable. More stable, that means here you can see in our complex plane, this is the S-plane, okay? So if we have poles here, say minus 1, say minus 0.5, another one is, say, 5 here. For this one, the corresponding is the exponential decay is e minus 0.5t. For this case, it's corresponding to the decaying rate is this one, is e minus 5t. So we say the system is more stable. That means the system decays faster to the 0 there. So this decaying slower, we say the system is stable but less stable compared to this one. So here we, using this technique, we can even quantify whether the system is more stable or not. So we call it relative stability. Okay. To do so, basically the way we can try is this. We simply apply the Routh Hurwitz criteria to the new axis here. So for example here, if we are given characteristic equations, let me call the f of s equal to 0. Okay, for example, f of s can be any example we've seen in our normal situation in today's lectures. Okay, so the Routh Hurwitz criteria apply to Fs is to determine the numbers of poles on the right-hand side of the S-plane. Okay, I would say right-hand side of S equal to 0. Okay, so that is our Routh Hurwitz criterion. That is what we have learned, which means we're discussing is we justify using this axis whether it's to the right or not. Now we want to study this one. Simply we tailored information of S for relative stability. That means for this case, answer these questions. Then what we can try is this. We simply shift the axis to here. So by replacing, let me say this new axis is S1. Okay. Let me call the new axis with a label that labeled by the indices S1. So basically S1 corresponding to 0 that align to S equal to -1. So from here the relation is this. You can see S1 equal to 0 corresponding to S -1. So that is S -1. When this is equal to 0, then S1, this one should be like this. You know what I'm saying? Do the replacement. So we can say when S equal to 0, then S is 0 plus 1, so that one S equal to 1, right? When S equal to -1 and -1 plus 1, this is S equal to 0. So basically you can see when we do the tabulation that corresponding to the scale. We simply do the axis shifting. Okay, so we do this one. Let me do that again. S1 equal to S plus 1. Or S equal to S1 minus 1. So basically here you replace, for example, say Fs equal, that is our given one, our given example there. So for example here we have our previous example about that. So our normal one. So say that is our first example, 5 plus 3s4 plus 2s squared 6x squared plus 6s plus 9 equal to 0. So do this replacement. Basically what you're going to do is replace s by s1 plus minus 1. s1 minus 1 fifth and plus 3, and s replaced by this one, s1 minus 1 4 plus 2, s1 minus 1 3, etc., etc. In this way, you obtained is f of s1 functions, right? And then once you have arranged the whole things, then you simply apply the Routh Hurwitz in terms of s1 symbols. Then basically what you justify is to tell how many numbers, by telling the sign change, then you can tell how many poles to the right of this axis. Okay? So the key thing is very easy step in studying the relative stability is you simply do the, here is called the shifting in axis, and that is a pure geometry. You can easily just like, just by observing this one and do the little replacement, you can tell how that relation will be. Okay? Okay, so I think in this way, we pretty much finished this module and module 2. So from coming, we will begin to go to module 3. And the homework, there's a 2 homeworks pending. Pretty much I'll give you plenty of time. I think the due should be, you look at the blackboard, I forgot, okay. And our test 2 covering majority is the module 2. The test 2 will be on Friday next week. Okay, so we can talk about that.